This is lecture number 10 of the course Engineering Mechanics, and in this lecture first we are going to learn what is meant when we say that a frame T is purely translating with respect to another frame F. A frame T is said to be purely translating with respect to F if the displacement of each particle of frame T or the RBT is identical over a given time interval. Further, that time interval is arbitrary. It can be anything. So, for any given time interval, every particle of T must be undergoing identical displacement. If that is the case, we say that frame T is purely translating with respect to F. So on this diagram, I am showing three particles fixed to frame T, and I am showing displacement vectors of these particles over a time, say delta T. This is the displacement vector of point B and this is the displacement vector of point C. If frame T is purely translating with F, then this must be identical. This is a more elaborate diagram of the same scenario. Here I have shown the RBT as observed from frame F. At three time instants, at t plus delta t1 and at t plus delta t1 plus delta t2. During the time t and t plus delta t1, I am showing the displacement vectors of point A here, displacement vector of point P here, and displacement vector of point C here. I am denoting these displacement vectors as delta R A, delta RB, and delta RC. And then observed over the next time interval of delta T2, the point A undergoes a displacement of delta RA prime, B undergoes a displacement vector of delta RB prime, and delta RC prime is the displacement vector of point C over time delta T2. A frame which is purely translating with respect to F will have this equation valid. And also during the next time interval, this equation valid. And similarly for all other time intervals that one may consider. Mind you, we are not saying that delta RA is equal to delta RA prime. This may or may not be true. What we are saying is that during a given time interval, displacement of each of the points fixed on the RB must be identical to each other. It follows that for a frame which is purely translating with respect to F, we will have the velocity of every point of the RB same. So A, B, C are the same 3 points on the RB, and we will have such equality. Every point has the same every point of RBT will have identical velocity with respect to frame F. And this is about time instant t. Based on what I showed on the previous slide, this equation and this equation, we can say that, so this equation leads to the conclusion that that's what I wrote as the first equation on the next slide. And it is easy to see why this would happen. Once you have this relationship, you divide each of these displacement vectors by delta t, and then you take the limit delta t going to 0. That will lead to this equation. You do the same two steps, divide by delta, should be delta t1. Here you divide, then you take this equation, divide by delta t2, and then you take the limit of delta t2 going to 0. We will arrive at identical velocities at t plus delta t1. T plus delta t1 follows from the definition of a purely translating frame. Thus, these are the two equations that I wrote here. Now, once you have these two sets of equation, we can conclude that the acceleration of point A with respect to f at time t will be equal to acceleration of point B with respect to f at time t and acceleration of c with respect to time t. Acceleration of c with respect to f at time t. Again, it follows from, it is straightforward to show. See, AF at time t is by definition delta t1 going to 0 VAF at t plus delta t1 minus VAF at t1 at t divided by delta t1. That is by definition AAF, and similarly you can write ABF as by delta t1, right? Now you look at this set of equation, look at this set of equation. It is clear that AAF must be equal to ABF, right? Because these two quantities are same and then these two quantities are same. Thus it follows that the acceleration of every point on the RB should be identical. So far we have concluded that velocity of every point on a purely translating frame should be identical, acceleration of every point on a purely translating frame should be identical. Now let me invoke the velocity transfer relationship. I want to write VBF using A as IP and T as IF. That leads me to this equation, what I have written here. B being fixed in T, this term is 0. We also know VBF and VAF are same. I have shown that on the previous slide. It means that this cross product should be 0. However, RBA is arbitrary. I can choose any two points. I can choose any pair of points on the RB and on the RBT, on the rigid body T, and I will end up having this equation. Right? So RBA is arbitrary in this equation, which means that omega TF must be 0. So a purely translating frame does not have any angular velocity with respect to the other frame F in context. That's my third conclusion. Just like I wrote the velocity transfer relationship, I also want to write the acceleration transfer relationship between points A and B. Using IF as T and IP as A, I write this equation. Right? ABF equals AAF plus 4 additional terms. We have seen such terms many times by now. I sweep from right to left. ABT is 0 because B is fixed in T. VBT is 0 because B is fixed in T. Same reason. Also, I know omega TF is 0 by now. Same reason, omega TF being 0, the double cross product will also go away. Further, I know ABF and AF are equal. I end up having a very simple relationship that omega dot TF cross RBA should be 0. Again, invoking the same argument that RBA is an arbitrary vector. It can take any value on the RB. And yet, this equation must be valid. What I am writing here, this equation must be valid for an arbitrary RBA. That implies that the angular acceleration of the frame T with respect to F has to be 0. So in summary, I have the following conclusions. If T is purely translating with respect to F, then VAF equals VBF, where A, B are any 2 points on the RB. Acceleration of A with respect to F should be the same as acceleration of B with respect to F, where A, B are any 2 points on the RB. Angular velocity of the frame T with respect to F should be 0. Angular acceleration of the frame with respect to B must be 0. Recall this relationship which we derived earlier and have used many times so far in this course. If A is an arbitrary vector, then the rate of change of A observed from F and from M are related through this equation. The difference is precisely the cross product between the angular velocity of a frame M with respect to F and the vector itself. If I now know somehow M is purely translating with respect to F, that leads to the conclusion that the rate of change of the vector A with respect to F is got to be the rate of change of vector A with respect to M. So two frames, a frame which is mutually a frame which is purely translating with respect to another frame will see the same rate of change of any arbitrary vector as seen by frame F itself. Sometimes in books we find a statement like what I have written here. An RB is moving with velocity 5 meters per second with respect to F, or an RB is moving with accelerations 10 meters per second square with respect to F. Now recall that we defined velocity of a particle with respect to a frame and acceleration of a particle with respect to a frame, right? P is a particle here. In the light of these definitions of VPF and APF, how do we interpret a language which is written in the way I am showing here? An RB is moving with velocity 5 meters per second. This sounds incorrect because velocity is always of a particle. Why are we associating velocity with a velocity vector with the entire RB? This sounds incorrect. Strictly speaking, this is incorrect saying that. However, if an RB is purely translating with respect to F, by now in this lecture we have seen that indeed in that case every particle of that RB has identical velocity. Every particle of that RB has identical acceleration, and thus in this scenario, when we know that a frame is purely translating with respect to another frame, this kind of language can be forgiven when somebody says the RB is moving with velocity or an RB is having so much acceleration. Since every particle of the RB is having the same velocity, it is okay to use somewhat of a loose language and say that the entire RB is having so much velocity. But please keep in mind that if the RB is not purely translating, this kind of language will not be sensible. It will not be meaningful. In fact, there is a problem that we discussed 2 classes ago. In that problem statement, they are using this kind of language. Let's read this. In the position shown in this figure, the thin rod moves at a constant speed of 0.1 meter per second out of the plate BC. They are talking about the velocity of not a particle but of a rod, of a rigid body. Not strictly correct. But then look at this rod. This is the rod I have shown in green color. This is the rod here. The way this rod is coming out of this tube, one can visualize that this rod RB4 is indeed purely translating with respect to RB3. It's purely translating with respect to RB3. RB4 cannot have any angular velocity with respect to 3. It cannot have any angular acceleration with respect to 3. It's like the rod is in the grip of tube BC. It cannot have any relative angular velocity with respect to RB3. So for such a scenario, such a language can be tolerated and is used sometimes by people. Moving on, we will start a new topic, kinematics of two RBs which are touching each other. Kinematics of two RBs which are touching each other. And we are going to talk about the definition of slipping or no slipping. Let us look at the diagram that we have on the right hand side of the slide. This is at time t. RB2 is touching RB1, and then there is an observer fixed to frame F. P2 is a point that belongs to RB2. P1 is a point that belongs to RB1. And at this instant, P2 and P1 are touching each other. If this inequality is holding good, if VP2F with respect to T is not equal to VP1F with VP2 with respect to F at time T is not equal to VP1 with respect to F at this time instant, we say that RB1 and RB2 are slipping relative to each other. We use this kind of language. We say that the two RBs are not slipping relative to each other at this time instant if the following two conditions hold good. There are two conditions for not slipping to happen. For slipping to happen, there is only one inequality that must hold good. For not slipping, there are two equalities, 1 and 2. What are these? First is Vp2f should be equal to Vp1f at the current time instant. This should hold good. Further, Vp2 prime f at t plus must be equal to Vp1 prime f at t plus. What is t plus? T plus is just after t. T plus is a time instant immediately after t. And what are P2 prime and P1 prime? These are two particles. P2 prime is still belongs to RB2. P1 prime belongs to RB1. But P2 prime and P1 prime are 2 points which get in touch with each other at t plus. Let's have a look at this figure once again. At this current time instant t, it is P2 and P1 who are in touch with each other. Whereas at this time instant t, P2 prime and P1 prime are somewhere like the way I have shown on the figure. They are not in touch with each other. However, at t plus, it turns out that P2 and P1 lose their contact with each other, and instead of P2 and P1, it is the pair P2 prime and P1 prime which get in touch with each other at t plus. That's the identity of P2 prime and P1 prime. And the second condition for no slipping is about the matching velocities of the 2 points P2 prime and P1 prime. If both conditions are fulfilled, then we say that no slipping is happening. But what if the first condition holds good? At time t, the 2 points in touching each other, they are having the same velocity, but at the next time instant, the 2 points that come in contact with each other are not having the same velocity. That's what I have written here. there is an equality here at time t, but t plus there is an inequality. If that is the situation, we say that the two RBs are in a situation of impending slip. Slip is impending for the two bodies. Alright, so we will keep these phrases, slipping, not slipping, impending slip, in our minds, and we will see some problems of interest later on. In those problem statements, you would find this kind of language being used, and accordingly, based on these definitions, we will deal with those problems mathematically. Now let's consider two RBs in a special situation. What is this special situation? I am talking about rolling without slipping. Rolling without slipping. Here I have shown a scenario of rolling without slipping. I have a cylinder. I'll call this body M. And this body is rolling without slipping on another body, which is F. At this current time instant, as shown on this figure, it is P1 interacting with P2, where P1 belongs to the body M, the smaller cylinder here, and P2 belongs to F, the bigger cylinder here. I want to know the following quantities. This is the quest right now. I want to know VP1F, velocity of this point on the smaller cylinder as seen by this man. I also want to know VAF. What is A? A is the center of this smaller cylinder which is rolling on the bigger cylinder. What is the velocity of this point? I also want to know the acceleration of P1 and acceleration of A with respect to F. It is given that the angular velocity at this instant, the angular velocity of the smaller cylinder with respect to the bigger cylinder is omega times k hat. Now mind you, k hat is a unit vector which is perpendicular to the screen here, but going into the screen. It is also given that the angular acceleration is omega dot k hat. So given this much information, I am interested in finding these four quantities. Again, knowing these four quantities, deriving and knowing these quantities would be helpful while we deal with problems of practical interest where one body is rolling without slipping on another body. So this derivation is useful in that way. Now on this figure I have shown some more details which we will use to actually find these four quantities of interest. What are those quantities? Those quantities are, I have shown a tangent unit vector. Tangent to what? Tangent to this green trajectory, green curve. And what is this green curve? This green curve is the trajectory of A with respect to F. I have shown a unit vector. I have shown the tangent, local tangent unit vector at A. I have also shown the local normal unit vector to this trajectory at this instant at A. And this En is pointed downwards. Alright. I will be expressing my final answers in terms of ET and EN. That's why I have identified these unit vectors. So all the four quantities that I want to find, they are all vectors. So I would need some unit vectors to express them. And these unit vectors are of my choice, En, Et and K hat. Let's start with VP1F. This is the first quantity that I want to find. But VP1F, according to rolling without slipping condition, must be equal to VP2F. That's what it means. No slipping. But then I know VP2F is 0. Why? Because P2 is a point fixed in F. And thus, it is straightforward to conclude that VP1F must be 0. Now let's try to find the next quantity of interest, which is VAF. Let's focus on this part now, VAF. Now to find VAF, I am going to use an intermediate frame M, and I am going to use an intermediate point P1. P1 is here. We will use the velocity transfer relationship, and that relationship gives me this equation. VAF is VP1F omega MF cross RAP1. RAP1 plus VAM. As usual, I sweep from right to left whenever I write a velocity transfer or an acceleration transfer relationship. I sweep the terms from right to left and mark them as known or unknown. Vam is known because A is fixed in M. RAP1, that is a known quantity. Look at the geometry here. This is where P1 is located. RAP1 is minus R times En, where this small r is the radius of the cylinder here, the rolling cylinder, right? So this is a known quantity. Omega MF is omega times K, the way it has been shown. That is also known. VP1F, we already know it is 0. So VAF turns out to be just this term, and when you put the unit vectors and take the cross product, it turns out to be omega times small r Et. So velocity of A with respect to F is pointing in this direction along Et, and its magnitude is omega r. So 2 of the 4 quantities I have found. Next, let's try to find AAF. AAF by definition is this rate of change of VAF with respect to F. VAF I have already found, previous slide. I get this. Now this has 3 terms inside. One is surely a constant with time. Radius of the cylinder doesn't change, but both omega and Et will change with time, and that's why you get 2 terms here. First has omega dot r still along Et, and the other term has omega r as the scalar part, and then you have the rate of change of the tangent unit vector with respect to F. 3 classes ago I did derive this expression while talking about the path coordinate system. The rate of change of the tangent unit vector with respect to time is this much, where s dot is the speed of the particle with respect to F. What is the particle here? The particle is A. After all, this trajectory is of A. So s dot is the velocity of A with respect to F. Do I know that velocity? Indeed I know. Previous step I know. From my previous step I know that S dot must be omega r. Then there is En. En is right here. We will keep that unit vector. And then there is rho. What is rho? Rho is the radius of curvature of this trajectory. Local radius of curvature of this trajectory. The trajectory of A. It is clear from the figure that rho is actually small r plus big R. Rho is small r plus big R. So if you assemble all these information here in this expression, we finally get AAF as what I have written right at the bottom of the slide. There's some obstruction here, so maybe I will write it here. The final expression is omega dot small ret. Acceleration has one component along et, still along et, and then there is another component along en. This is AAF. And mind you, in all my lectures, all these symbols mean the same quantity. I mean to write small r, but I end up using one of the three variants of small r. Please keep in mind that they all are the same things. There is no difference between these three symbols. So by now we have been able to find three of the four quantities of interest. I have been able to find this, I have been able to find BAF, I have been able to find AAF. Next I want to find acceleration of point P1, which is the point of contact here with respect to frame F. We will do this derivation in the next lecture.